Okay, so today's topic is teaching the computer to talk to us in some way or another. Done. So, the most common way to teach a computer to speak to people is using a function called printf. So I will share my screen and let's check out. So the most common way for computer to speak to us from the code is using printf function. So have you used printf in your life?
Yes, sir.
Okay, so in Arduino, it's called serial print or something like that, but that one is actually limited. This one is a little bit, I would say, better. So the function itself is just printf, and then you type the text that you want to print out. But now we will, so I don't know, there should be some example code. For example, in your code, you write printf, then you write the text that you want to print. And if the text has special %sign characters, then you can also print out some numbers or texts, and these things will be automatically formatted and then printed out. So about printf, you will study more in lab. You will check out what you can print and what you cannot print and how the output looks and what all the specifiers are. But in this lecture, in the theory, we will talk about how exactly these letters travel from microcontroller to the PC or to your computer. Okay, and the transmission of these letters are mostly usually done using a peripheral which is called Uart, Universal Serial Universal Asynchronous Receiver Transmitter, and it happens in the following way. So first of all, the computer where is it? So first of all, we need to make the physical connection between microcontroller and the computer. So here will be our microcontroller. And the microcontroller has a special peripheral inside which automates data transmission for us. And it's called Uart. And it is able to control two microcontroller pins at the same time. One of those pins is called TX, and that is the pin which sends the data out. So data goes out from TX, and the second one is RX. This is where the microcontroller receives the data. Okay. And the computer PC, old PCs actually had this UART port built into them. It was called serial port. And it looked something like this, like in this picture, this one. So you could just take cable and connect it to TX of this computer and the second wire and just connect it to another pin, and the other ends of the wire connect directly to microcontroller, and in some cases it would just work. Okay. The only thing is that this serial port had high voltage. It was something like 15 volts of voltage on these lines, but the microcontrollers, older microcontrollers work from 5 volts, and newer microcontrollers work up to 3.3 volts or 3.6 volts. Therefore, this direct connection would actually possess a risk of burning the microcontroller, right? But theoretically it would work. And then nowadays, since the computers are becoming smaller and smaller, and the ports are becoming also smaller, usually in 99% of cases, there would be a converter which converts UART to USB, and you can just buy them in the internet. So I'll just put the box here. And just connect them directly. So I will write UART to USB converter, just a schematic with a chip on it. And that one connects to the PC using a USB cable. Okay, so there would be your PC. Personal computer or laptop or Linux or Macintosh computer, whatever. So USB connection. And inside the computer, in the device manager, you can actually check out how many USB to UART devices you have. For example, in my computer, I have right now plugged in the development kit, and under ports, it will be this COM port number 56. So this is actually not a real UART port, it's actually a USB to UART converter, but Windows shows it like it's just a UART output port. Okay, and here's the important part. UART has TX and RX lines, so obviously one device TX connects to the RX of the other device and vice versa. So UART to USB converter has written text RX, and it always connects to microcontrollers TX, and TX of the UART connects to microcontrollers RX. Okay, so just a thing to remember, but unfortunately, oftentimes many manufacturers of some devices, they actually write the wrong text here. Oftentimes on their devices, they would write that instead of RX, which is the receiving end, they would write TX so that you would connect TX of the other device. So, and on the TX side, oops, I wrote the arrow to the wrong direction. On the TX side, they would write RX as if they're telling you to connect RX cable of your device to this port. And that oftentimes creates a confusion, and that is bad. I'll just show you an example. Okay, so one company asked me to build a cable. And let's see which one it is. To 170 kiosk. Okay, so so for example, this company ID Tech, they sell these card readers. So you connect this device to your computer, for example, and this device accepts payment cards in a secure way. It's glued closed so that nobody can break it open and tamper with it. Most probably this plastic case also has a button inside. Oftentimes that's the case. There's a button, and when you open the case, the button releases and the device marks that it has actually been tampered with. Okay, so these devices they might be built in such way that you cannot really open it without being noticed. Either you open it and the button releases and the microcontroller marks it, or you have to cut it open around the button so it doesn't get released, but then you damage the outer shell. And obviously people who want to pay with a payment card, they would see that this device has been opened. And inside you would ask, well, how does this device know that it has been opened if it has, for example, power switched off? Oftentimes these devices have a small coin cell battery which is connected to microcontroller, and it's normally off, but when an event happens, for example, somebody presses the button, the microcontroller wakes up from the battery and writes into its memory that the button has been pressed, and then goes to sleep again. So there, oftentimes inside there's a small coin cell battery. It doesn't work from that battery all the time, only when the button changes the state.
So
Okay.
is it like interrupts?
One more time.
Is it like interrupts? Like interrupts, some function that are triggered in middle of code, like when the microcontroller is sleeping, and some function triggers
Yes, yes, yes,
for
yes.
interrupts.
I understood you now. Yes, interrupt happens exactly as you say. Microcontroller has general purpose input output interrupt on that pin, and it wakes up on that interrupt. Yes. Okay, and now let's check out. So there is this data sheet. Basically, you can just go on the internet and buy this thing. You know, it's not a secret thing. And in this device, for example, you have some data about, for example, how long will this device work, their estimates. So a median time before failure. So 500,000 hours at plus 40 degrees Celsius. So when you buy it, you know that it's not going to break after like 2 months or something. So it's 50,000 hours. Let's check out how much it is. Actually, it's, you know, it would be interesting for me to just check out 500,000 hours divided by 24 hours per day divided by 365 days per year. So they say that this device will work for 57 years. Okay. How is it possible? Well, probably they don't have electrolytic capacitors. Maybe the PCB is actually painted with a paint that doesn't allow a moisture to get onto these components so that the metal doesn't oxidize and doesn't rust, right? So, you know, some engineering can actually make it possible, okay? And then there are other data about voltage, how much voltage you would you would support. And now let's check out the connectivity. So we want to connect this thing to our device. Let's check out information about connector. And here it is, connecting to the data port. So you have two options. One is USB through USB connector, or RS232 through the Molex connector. Actually, this is not a Molex connector. It was actually Hirose connector. So that's one failure. But let's say your embedded device doesn't have USB. So if you want to connect it to a computer, you would just use USB cable and that's it. Because computers have USB and don't have RS232. However, if you are building a device using a microcontroller, microcontrollers usually don't have USB. Only more expensive ones have, and then you have to write a lot of software to manage all the USB events. So that would be just a more expensive device. And in many cases, people just use microcontroller. Microcontroller has RS232. And here is the problem. So I knew that it is possible to happen. So I just warned the client that this might be the case. But here we can see RS232 connector names. So they say that pin number 1 is RS232TX, and pin number 3 is RS232 RX, right? So the correct way to write is, this is TX pin through which the device sends out the data. This device should send out data through pin 1, and through pin 3, it should receive data. But unfortunately, the manufacturers have mixed these names up. They think that they need to write that you connect your device's TX to this pin, and to the pin number 3, you connect your device's RX, right? And so when I first built the cable according to the correct way, these lines were in the wrong order, so the tester had to swap them, and then everything worked. So the correct way is that you mention your name, your device's functionality. So this line, for example, TX sends out and RX receives in, and the other device writes, this is my RX pin through which I receive, and this is my TX pin through which I send out, and you connect TX to RX and the other RX to TX, and then it should work. But just be aware that manufacturers oftentimes make this mistake and swap these. So you test in one way, and then if it doesn't work, you just swap these cables and test it the other way, okay? So, and another thing is that oftentimes these lines actually don't work at 5 volts, but only at 3 volts, okay? Because, for example, this microcontroller, it has some power supply. Okay, I'll just draw it here. So all microcontrollers have some capacitor to smoothen out some bad power supply noise, right? And here is the power supply, VCC, for example. Oh, I'll write it with the text tool. That will be better, VCC. So some power supply. Oftentimes, for example, this UART USB converter, it can provide USB voltage, which is 5 volts, right? I'll just write in example 3.3 volts. 3.3 volts is a very popular voltage. These USB to UART converters, oftentimes they provide 5 volts out because that's the USB voltage. So you can also not use it if your microcontroller is powered by some other source through battery or from mains, but oftentimes you can actually take power from this UART to USB. The limitation is something like 500 milliamps max, no more than 500 milliamps, and it gives out 5 volts. And of course, these lines, they give voltage relative to ground. So always in all UART connection, the third cable is the ground cable. So, okay, the correct way would be to draw it like this. So from this USB to UART converter, the line goes to the microcontroller, but the connection is actually made to the ground. So actually all UART connections have at least 3 wires, TX, RX, and the ground. and sometimes you can use this power supply. Okay, so these lines, their voltage, now we need to talk about that. The line voltage is oftentimes 3.3 volts. You can measure it or you can try to find it in the datasheet, but mostly these lines are driven directly from the microcontrollers. So in this UART to USB bridge, there's also actually a microcontroller which receives and sends the data and converts it to USB and sends to USB. And these lines are usually, 3 volts, 3.3, or maybe 3.6 volts. They can also be 5 volts, but you have to be aware of that. So the microcontroller has a limit that it can only accept from 0 to 3.3 volts. So if you know that these lines might have higher voltage, for example, maybe this UART to USB bridge works from 5 volts, then you cannot directly connect them, but you have to insert a voltage level translator in between, okay? And so I have to mention these chips. Let's check out ST2323, or is it? Oops. Let's see, maybe it is this one. So the manufacturer doesn't matter because these chips are built by mostly any company, but these chips basically are, for example, level converters and also level acceptors, which translate whatever voltage you are controlling to, for example, 5.5 volts. And the other and the receiver also has this chip, so it doesn't care if you have 3 or 5.5 volts. This chip accepts any of these volts and gives low or high relative to local power supply. Okay, so this is kind of a flexible level converter. So let's check out their basically their picture. This one is not so great. Usually, I like Texas Instruments because they oftentimes have better data sheets. Texas Instruments Max 3232. Yes, that's the name. This Max 3232. You can check it out in, for example, Octopart, and you will see that with this part number, you have Texas Instruments is manufacturing this chip, Maxim Integrated. I think Maxim Integrated was the original maker of this chip. This is why it begins with Max. And then later, when the patents expired, now everybody can manufacture this. And Texas Instruments, Maxim Integrated are not the only ones. Other companies also make this chip, and let's just sort it by lowest price. And yeah, it costs something like from €1 to 50 cents, depending on the quantity. For example, this Renesas also makes it. Let's check out what this thing does. So basically, this is a simplified schematic. You can supply it from 3.3 volts or up to 5 volts. It has a built-in capacitive boost converter so that it creates its own 5-volt output. Then it drives the output lines with 5 volts. And for the input, it receives from 3 to 5 volts, and it converts it down to your microcontroller's voltage levels. So the microcontroller puts in whatever voltage level it has, 3 volts or 5 volts, for example. This thing sends out 5-volt levels, and the other end receives 5-volt levels, and using the same a second chip like this, it can down convert it back to its levels. So it operates from 3 to 5.5 volts. It consumes 300 microamps. So this is not a low energy converter, because anything that is above 5 microamps is not considered battery operated. So 300 microamps would eat your battery over several weeks, right? So this is more for devices that are powered from mains power constantly, but you know, that's life. It also says the maximum output speed that it can send is 250,000 bits per second. So, you know, you can't work with megabits per second, for example. That's your limitation. And these chips are very, very popular. If you, for example, if you're building a device that communicates with outer world, usually you would use this chip on the output because it also works as over voltage, over current, and ESD protection device. So even if somebody touches these lines with electrostatic finger, right, charge, for example, with a synthetic sweater, that chip has ESD protection of 15 kilovolts, and it accepts this ESD and doesn't let the the chip be destroyed. And so in our picture, I'll just copy it and paste it right here. So in our picture, this chip would go here in between the lines. Oops. Down. Mm-hmm. Huh? Mm-hmm. Oops. So both of these are level converters. Mm-hmm. And with these level converters, you can actually put these devices further away. The cable can be also longer. The cable still has the 3 lines, TX, RX, and ground, but at least the levels are synchronized. So I'll just write it here. TX, next line is RX, and like next is ground. And here RX, TX, and ground. Mm-hmm. And in this case, it works in single-ended mode. For example, in this case, the line voltages are 5 volts. And for example, this UART to USB converter, its internal supply voltage is oftentimes 3.6 volts, for example. So even if they are different, the devices can communicate because there are these voltage converters. Of course, they cost money, but you have to put them. And in this device, most probably, it also has these voltage level converters. You cannot really know it in advance because this device doesn't, its datasheet doesn't really say the voltage levels on the UART lines. So the only thing that you can do is you have to first buy one and then measure with the voltage level of these pins. And if, for example, I measured it and it said 3.3 volts, and my microcontroller is also working from 3.3 volts, then I wouldn't put these level converters. But it measured 5 volts, so I had to put a level converter before microcontroller, and only then it worked. Okay, But for example, in our labs, in our development kits, the UART to USB converter is built in the development kit, so it connects directly with microcontroller. Okay, so it connects directly and no level converters are necessary. But here they are there. And yeah, so this is about UART. And some fun facts or important things that you need to know. First of all, Uart lines are idle high. So by default, the levels of TX and RX are high. And when you send the data, you have to pull them low to send 0 and high to send 1. But generally, this is why all messages start with 0, so that the receiver detects that, oh, the line went low, so somebody is sending something to me. So start bit is always low. So what is the reason for UART lines to be idle high? Well, the reason, I can just tell you one reason, is if you disconnect the lines, both ends feel that the lines are not held high, so the other end is not connected. So because UART lines are idle high, you can detect whether the cable is connected or not. So the transmitter, I will draw a red circle around it. Transmitter is the output. It controls the line level and it sets this TX to RX line high all the time. So when I connect the second device, it senses on the RX line that the line goes high, so it knows that something is connected to the other end and you can communicate, and vice versa. The other party's TX line is the one that is active and is holding the line high. So when I connect the cable and the other end feels that RX went up, it knows that the cable is connected and you can communicate, wait for information. So UART lines are idle high so that the device can detect that it has been connected to something or that something has been connected to it. Okay, as a result, first bit is always 0 and it's called start bit. Okay. So all messages start with a bit which is called start bit. Next thing is, and we can check out it on the internet. So start bit is low and you detect, okay, so here begins a message. Then you can have the data bits, and the original UART had 7 data bits. Oops. So I will write 7 data bits right now because the first communication really used just 7 data bits. You are used to normally have 8 data bits, right? 1 byte is 8 bits. But initially, in the first networks, these lines were used to send text. So, for example, to connect to the internet, you go to web pages, but the web pages are written in HTML, in hypertext markup language, which is just text. You know, you can go to this page, you can view page source, and you can see that actually this is just text. This text describes how to draw the page and where to put all the information, but generally it's just plain text. And if we check out the plain text, there's only 28 capital letters in English language. So it's 28 capital letters plus 28 small letters in English language plus numbers from 0 to 9 is 10 numbers plus, and then you have some special characters like exclamation mark, column, single quotes, double quotes, and let's say these are, for example, another 30 symbols. So another 30 symbols, and you can see that practically everything that you see on this page, the characters, there are only approximately 100 characters. I think that ISO keyboard only has something like 100 keys, right? So with shift you can get more letters, but generally the keyboard has approximately 100 symbols. So you don't have to really send 256 bits because you can fit all of the English language letters and symbols in just 7 bits, under 128 bits. And it is done using ASCII table. You can check out it on the internet, and here it is. So basically it gives a number to each letter, and actually it sends numbers over the internet. And using this ASCII table, you can, you, for example, receive number 60 on Uart, and you find in this table that 60 is actually this sign less than, okay? So actually numbers are sent over Uart, and because in English language, all the letters, all the brackets, delete button, space, exclamation mark, everything, new line symbol, all of these symbols, there aren't really that many, and it's just 127 different symbols. You can fit them, 128 different symbols counting from 0. You can actually fit them all in just 7 bits. So initially, Uart actually used 7 bits. And here is why. Another reason. So I'll just put it in Uart, or better say RS232. So if you can send all the data that you need in chunks of 7 bits, you shouldn't really send 8th bit always 0 just to fit 1 byte. Because if you can send text in 7 bits versus 8 bits, let's check out. So let's see what the ratio is between 7 divided by 8. So 7 divided by 8 is 0.875. So if we send, instead of 7 bits, 8 bits every time, our data length would increase by 12.5%, but we wouldn't really be sending any useful information. And imagine 30 years ago, internet was so slow that this trick increased virtually internet speed by 12.5%. Just sending 7 bits instead of 8 bits increases the speed of communication by 12%. You know, in modern days, we don't care because we have optical internet, high speed, Wi-Fi, 5 gigahertz, and speeds are now in gigabits per second. But the original Uart used for example, DSL, its speed was only 9600 symbols per second, bits per second. So it was really, really slow. So by sending 7 bits instead of 8 bits, it was actually much more usable. It was 12.5% faster than it would be if 8 bits were sent out of the principle. Okay. Of course, nowadays, to send data over the internet, people are using Ethernet. So UART doesn't really, isn't really used for that anymore. So nowadays, of course, people are practically always sending 8 bits. 8 bits. Usually all communication uses just 8 bits and that's it. But oftentimes in the microcontrollers, you can configure it that it sends from 4 up to 16 bits in single line. For example, if you are building some kind of device with some proprietary connection and you're not going to connect it to the computer, just to other devices, you can also make it be 16 bits during each transmission. Okay, so after sending data bits, let's say, after sending data bits, for example, here it's 7, it's 8, for example, 0, 1, 2, 3. If you count from 0, then it's 8 data bits shown here. After them, you can put in either a parity bit, so either even or odd parity, which is optional. So historically, after sending data bits, a parity bit would be inserted, and you can find info about the parity on the internet, parity. But in computing, parity bit, here it is. Okay, so you send, for example, 7 bits, and the parity adds 1 to make it the number of bits either odd number or even number. So, for example, you send these bits, you count how many ones you have, 1, 2, 3, 4 times you send 1. 4 is an even number, so you don't add 1, you just add 0 as a parity bit. Or if you have decided that you will use odd parity, you would put 1 to make the number of ones odd, right? And this is usually, so it doesn't change over time. You, for example, create a communication channel, and initially on the first day, you decide whether you will have parity or not. And if you have, then you will have even or odd. And then you write it in your device's datasheet. And if somebody buys your device and wants to communicate with it through UART, they just check out in the datasheet whether it's even parity, odd parity, or no parity. In older days, it was actually very popular to use even parity. And between these parities, somehow, at least as far as I know, even parity was kind of more popular, right? But here's the problem. Let's say with the parity, let's say I'm sending 1, 0, 1, 0, 1, 1, 0, 1. Let's say I send 8 data bits. And let's calculate parity. So let's calculate even parity. I count number of ones, 1, 2, 3, 4, 5. So 5 ones. Since I need even number of ones, but I have odd number of ones, I need to add 1 to make the number of ones in total even. Even number divides by 2. So 1, 2, 3, 4, 5, 6. Now I have even number of ones. But here's the problem. What if I send this message, but during the transmission, an error occurs? So I send it, right? But during the transmission, one of these ones became 0. The receiver counts ones, 1, 2, 3, 4. it sees the number of ones is already even. So, and here is an extra one, which makes the number odd. So it knows that this message had mistake, and it can reply that there was a mistake, or it can just discard this byte. So it works if number of mistakes is one mistake. What happens if 2 bits during the transmission are flipped? Let's say, for example, I sent the message, but 2 ones got low. So the receiver counts 1, 2, 3, 3 ones to make it even 1 at the end. So for the receiver, this message, which has 2-bit errors, looks fine. So this is false positive. So if you just run through your head the math, parity only catches 1, 3, or 5, or 7 mistakes, but it doesn't catch even number of mistakes. So in total, parity has only 50% chance of detecting a mistake, right? So, and if, for example, one of these zeros becomes 1 and the other one becomes 0, I have 2 different mistakes, but the parity will be calculated as if it was correct, and the mistake wouldn't be detected. As a result, in most modern architectures that I know, parity isn't really used. So in newer channels, in newer transmission protocols, parity is not used because it's weak. 50% chance that a bit flip or something like that will not be detected. So don't use it. Don't think that, oh, you're turning on parity so you don't have mistakes. Actually, you might have even bigger mistakes if you have parity turned on. So best thing is to do is just send something like all the bytes that you need to send. You need to send, for example, a message with 20 bytes. Send those 20 bytes, calculate a cyclic redundancy check, and send it. And then the receiver detects all the mistakes with a very high probability, much higher than 50%, something like 99.9%. So parity, not recommended for new designs, not good, not safe. And after sending bits and or parity, there is a stop bit, which is 1 bit, which is high. Because, for example, if you need to send several bytes, you would send, for example, oops. So, for example, you need to send 1 0 1 1 0 0 1 0, and then the second byte that you need to send is 0 0 0 1 0 1 0 0. So when you send these, so the line goes like this. The idle line is high. Then before sending the first bit, the transceiver sends start bit, which is low. And only then it sends 1, 0, 2 times 1, 2 times 0, 1, 0. And if, for example, there wasn't a stop bit, then it would immediately start sending the next byte. So low, 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 high, low, high, low, low. But the problem is, if you're sending a lot of data and senders and receivers reference clocks are a little bit off, then it might happen that the receiver, for example, samples these bits a little bit too fast, and these bits start to shift into the wrong positions, right? So this is why after all 8 bits, there is this stop bit. So for 1 bit period, you have to hold the line high. And only then when it expires, then you send the start bit and the bits after that, okay? Because between the sender and receiver, there is no synchronization clock. So you might ask, well, how does the receiver and sender know how long each bit is sent? So I'll just put some text. So I'll put start with small letters and stop. This will not use parity because I don't recommend it. So I will rotate it back and I'll rotate it this one back. Let's just put them. So start bit goes here. And here, this is start. And stop bit goes here. Ugh, give me a break. Oopsie, I cannot point to it. Okay, so stop bit is here. And the second stop bit at the end of the second byte. So it happens like this, and then the line goes idle again. So I sent 2 bytes. Okay, so the question is, how many bits did I actually send? I sent 8 data bits, but every time I want to send 1 byte, I need to also send the start and the stop bit. And parity bit would just add extra length, but only have 50% chance of catching the error, so it's not used. So in total, to send 8 bits, I actually send 10 bits in this case. And in most modern communication channels that are using UART, it's the same. It's 1 start bit, 8 data bits, and 1 stop bit. But theoretically, some networks use 2 stop bits so that when you send the bits, 2 stop bits, lets the receiver kind of manage the byte before it's being thrown a new byte in. So 10 bits in this case, and the next transmission also has 10 bits, and with UART you only send byte by byte, so 10 bits. And this is why the speed in UART communication is expressed in bauds. So 6th is stop bit to the text, and and 7 baud rate is not bit rate. So each of these impulses is called baud. I don't know why, but it's called this way. So bits are the ones that we send, but start and stop aren't considered data bits, so they are called bauds, all of these impulses. So in our case, we have what we tell is the time for each of these impulses, low or high, and it is called baud time or period, and how many bauds per second we have is the baud rate. And the, one of the initial baud rates was 9600 bauds per second. And as I said, bauds include start and stop bit, and maybe also parity bit if it is used. So let's assume that in our case, it's just start and stop bit. So if we divide the number by 10, we will get how many bytes per second. So 9600 divided by 10 equals 960 bytes per second. And if we multiply this by 8, divided by 10, multiplied by 8, we get only 7,680 data bits per second. This is something that you need to take into consideration, because this speed would actually be very slow. And now I'll just write some text in this character counter. And I write, for example, it says 3 characters. I write the text, for example, hello, my name is Andris. Let's count characters is 24. And the question is, how long will it take to send at this speed this text? So 960 bytes per second. So it's 24 divided by 960. It will take 25 milliseconds. And it's actually not that short time. Web pages have thousands of letters, so that would be really slow. In modern communications, so in some old devices, they use this 9600 because it's, just industry standard. You take some old robotic industrial device, it's using 9600. So the newer devices also have to use 9600. Also, the speed is slow, so you can have long cables, and you don't have to really worry about the speed impact on the cable length, because the speed is so low that you can send this slow signal over, I don't know, 1 mile of a cable, and maybe at the other end you wouldn't really notice any significant distractions in the signal. But in shorter connections and in microcontroller world, a very popular speed is 1.15200. Let's check out 9600 times 2. Okay, this should have been a multiplied number. Okay, so it's 12 times faster than this 9600. Usually Uart, for some reason, uses multiplications of this number for the speeds. So oftentimes you open a data sheet of some device and it says the speed is 115,200, and you might wonder, why not just 100,000 bauds per second? Well, because somehow they use the multiplication of this number of 9600. This is a very popular speed, 115,200, used mostly everywhere in newer communications. And yeah, and it's 12 times faster, so it's good. So this speed is popular. And our development kits also are using this speed for their built-in UART to USB cable. And oftentimes you buy this UART to USB converter to connect to PC, and it has just fixed speed. Sometimes you can adjust the speed, but sometimes not. And so this is how you send the signal. And now I will mention some special cases that have derived from UART. UART is a very good communication channel, and most everywhere it's still used because it's really simple and microcontrollers support it. And in microcontrollers, you first configure UART with the speed, and you have to set the microcontroller's UART speed the same as the other end's UART speed, and it is just documented in the either datasheet, and then you just send the data forth and receive it back, and everything works. And in microcontroller, you just give UART peripheral a new byte to send, and it just sends it out, and it sets a status bit in its register that it has completed sending. And when it receives data, it can make an interrupt in microcontroller and give it the new byte that it has received. You will do this part in lab. I can talk about it all day. You will not get smarter. You just need to try it out in real life. But now I'll just mention some special cases of UART. So first thing that we can notice in this is you cannot connect multiple devices here because each device has RX and TX, and if you want to connect a third device, you can't. Okay, so the third device also has just TX and RX lines. Right, so if you would connect, for example, TX to microcontrollers RX, there would be conflict between these two TXs because, for example, one is driving line high and the other one is driving line low, and there would be short circuit, and I don't know, maybe cable would burn, maybe the UART pin would burn, and nothing would work. There would be bit errors at least. So you can't really connect it to the other line because then the microcontroller will not hear it because it's sending out through the same. So basically UART is point to point, and you cannot connect multiple devices on these lines. It's just one device connected to another device. But based on this UART, there are some other communication methods that actually allow multiple devices to be connected. So let's check out RS232. What is this RS232? So RS232 is a standardized communication mode using the serial line. Let's check out. It has several versions, and you can see that its voltage levels are not 0 to 3 or 0 to 15. It's actually negative to positive. Okay, so when the line is, for example, idle, it outputs some negative voltage, and when it sends, it sets to a positive voltage. The reason for it is you get a higher amplitude of the signal, so you can send it over longer lines, and you get longer distances with this. So higher amplitude means it's a more prone, it's less prone to some noises, electromagnetic interference, and the voltage levels is de-asserted, or one is -3 to -15 volts. If it's -2, it means that the cable is too long, it cannot drive it properly, and 0 is at least plus 3 volts, but at most plus 15 volts. And again, you cannot connect these lines directly to your microcontroller. You need a level converter, and of course you can buy a level converter. For that, just a different part number, RS232 to MCU converter. You can buy them, but you just have to make sure that you buy the correct one. For example, this one wouldn't really work because it doesn't accept negative voltages and doesn't generate negative voltages. Let's see what are the output signals. I think it only converts from, oh no. It actually generates a negative voltage. Yeah, that's right. Then this chip actually works. Well, its name actually suggests that it should work because it's max 3232, so it should output 232 voltage level at the output, and it actually does it. So idle is negative voltage, and when you set it to 0, it outputs high voltage. And it says that it should be at least -3 and +3 volts. I'm not sure if the amplitude can be set higher, but generally, yes, it converts. With these capacitors, it uses a capacitor charge pump and it changes the levels to positive and negative. So it actually also outputs, oh, here's the application curve. Yeah, so it outputs also negative voltage. So I'll correct my picture here. So actually, with these level converters in RS232, the real RS232, it's actually under -3 volts to over 3 volts. Yes, so as you can see here, when the line is idle in the microcontroller side, the output is -5.7 volts. Then you set it a low, the output changes to +5.7 volts. So this thing generates, it doesn't generate, as we saw here, it generates something less than -3 volts, so it's minus almost 6 volts. And here, something over 3 volts is plus almost 6 volts. So this thing sends the signal this way. So you definitely cannot connect its output directly to microcontroller. You need to connect it at the other end to the same chip so that it converts back to microcontroller levels. Okay. And the result is that you get a higher voltage swing. So the signal is more resistant to some noises that you might have. So this is a very popular chip. Most probably you will use it whenever you connect an external equipment to UART. On the PCB, you don't use it between two chips on the PCB, but over anything that is cable-like, you would use this chip. So RS232 is this thing, okay? And the next thing that is derived from RS232 is RS485. Its principle is very similar, but it's used for longer lines, and you can send and receive data over the same line because it's differential, but you cannot send and receive data at the same time. But the message structure is the same, so you just have differential line. So start bit is sent first so that the receiver and transmitter know that they're sending something, then you send the data bits, and then maybe there is parity, but usually there isn't, and then there's stop bit, and then it's idle. And this is also standardized so that, you know, people use the same voltages and everything. So Max linear technology. So Max 483 also creates these levels. And here is a big advantage to this differential mode. You don't really care about what the absolute level of voltages is. It's just that if one line is more than 200 millivolts higher than the other one, you read it as binary 1. And if the other line is a little bit just 200 millivolts higher than the first one, then you read it as 0. So that's pretty convenient. You don't care if it's +5 or +15 volts. It's just that one needs to be a little bit bigger than the other. But the disadvantage is only one device can speak at the same time. So usually either you send data rarely, so two devices don't talk over one another, or one of the devices is the master, which just asks questions to devices using, for example, device unique ID, and then only the selected device with the appropriate unique ID responds. So you have kind of network here. And in pictures, so a typical picture is like this. So the data lines are called A and B. A is like the negative one and B is the positive one. And they just connect in parallel. And also, of course, you have ground connected so that, you know, they are referenced to each other. And this thing can be driven from 0 to 3 volts, for example, no problem, because it's differential signal. And for this, you can use chip called something like this. I think it's Esd 485. So again, you connect it to microcontroller, and the other end you connect to the data cable. And on the opposite end of the cable, the other device also has this chip, which converts back the signals to microcontroller. And it has the receive output through which it sends received data to microcontroller. So here data goes to microcontroller. Then you have a switch with which you enable or disable this buffer. Usually people just have it turned on all the time. Or they switch it off when they are sending out. So actually you control it. Then the second signal is enable transmission. So you only set it high when you want to send the data out. For the rest of the time, it's switched off. And then data in. This is the TX of the microcontroller with which it sends the data to the lines. So in idle, A line is low, B line is high, and when you turn on the output and send the data, these lines are switched in opposite manner, and the other end receives the data. But with this configuration, you cannot detect whether something is or isn't connected at the other end, right? So, and this read enable and data enable, they can actually be connected together and used as a switch. When it's high, you are sending, and when it's low, you are listening on the port. And these chips are, again, very good. They come with protection. They accept from -7 to +12 volt as input, so you don't care if it's differential negative or something like that voltage. And also they have ESD usually. They have some information here usually about electrostatic discharge tolerance, because when people plug the cables in, maybe they are charged with the static electricity and it can discharge into the device and destroy it. So these things actually usually have ESD protection. Let's check out ESD. Well, it doesn't say anything. Let's say kilovolts. Can't find any information right now, but usually they're prone to that. If not, then you have to attach an external ESD protection diode. Otherwise, you can accidentally destroy your chip and then it doesn't work. Okay, so that's about it. And finally, there's one thing that I need to tell you about Uart Lines, which kind of corresponds to what I told you in the previous lesson. So let's say that you have a device and on the board, for example, microcontroller needs to talk to some sensor, and the sensor is built in such a way that it talks over UART. I'll just use this picture. Just a fun fact for you. So, and instead of USB to UART, it's just going to be sensor. For example, I can just give you an example. There is this, for example, CO2 sensor, which measures the carbon dioxide level in the air. It says how many, how much breath is in the air. So, but it's built in such a way that it it reports over the UART. So you send it, hey, what's the CO2 level? And through UART, it replies that the level is, for example, I don't know, 500 or something. So now let's check out. Usually these sensors are not low energy. They consume some power. For example, they consume, I don't know, 20 milliamps. But you want to build a device that runs from the battery. For example, you want the device to run from the battery. So what you can do is you can put a MOSFET, P-type MOSFET in the supply line, and you can switch it on or off using this MOSFET. I'll draw it here. So you want to switch off the MOSFET. P-type. And you control this gate. When you set it high, the chip is off, and when you set it low, the MOSFET is turned on. It supplies power to this sensor, and you can do the measurement, and when you have measured it, you just switch it off, right, with this P MOSFET. But here is the problem. How do you think will this schematic work? Well, it will work. I can just guarantee you that the sensor will be supplied. But the question is, will it turn off when you switch off this MOSFET? How do you think? So basically, when the MOSFET is on, it's supplied, the sensor is supplied, and it works. And when you switch off the MOSFET, I'll just, I'll move it out of the picture so the power supply is shut off. And the problem is that sensor keeps working. What is the reason? For example, you have a battery, you measure the current through the battery, you tell the microcontroller to switch off this P-channel MOSFET, but even with switched off MOSFET, you see that the current is still 20 milliamps. The sensor is still working. Maybe it has an LED which is blinking. but you don't understand what's happening. And you take a soldering iron, you think that maybe this P channel MOSFET is damaged, so you solder it out, you remove it completely from the schematic, you turn on the device, but the sensor is still working. Why?
Because you said initially that the TX and RS have power.
I'm sorry, can you write the answer in the chat, because there's some problem with the sound. Chat. Okay, so you can write your guess in the chat box. You have received the power supply. Yes, so this is the correct answer, because as I said, TX and RX pins have voltage. The thing is that in this in all devices nowadays, including the sensors, the pins have ESD protection. So I'll zoom in and I'll draw small ESD diodes here. So each line, for example, this TX line, it's high, it's 3.3 volts. And before it goes to the sensing element in the chip that is built in, to protect it from electrostatic discharge, there is a pair of electrostatic discharge protection diodes like this. And it actually exists for both lines. All lines of all chips nowadays have ESD protection diodes, which connect each pin through a diode to power supply and to ground. As a result, even if you have disconnected the power supply, the UART TX line is high. So here is 3.3 volts, the CPU power supply is 0 volts, and the electricity, the current, flows from the TX line through this protection diode to chip's voltage supply, and internally actually supplies the sensor with the power even when you have disconnected its main power supply from power. Okay, so, and usually these sensors, they also have a capacitor. You know, all chips have some noise reduction capacitor between power supply and ground. So through TX line, you charge through this protection diode the sensors decoupling noise reduction capacitor. And then from this capacitor and from this TX line, all of the sensor is being supplied by power. So you can actually calculate, because the voltage drop on this diode is approximately 0.6 volts, then instead of 3.3 volts, here will be 2.7 volts. But at this voltage, this thing will also work. So the solution is, and I've seen it many times in many shapes and forms, what you have to do is when you switch off the sensor, you also need to set the connection lines low so that there's no power at the input and also no power through the data lines. And I have seen this oftentimes. For example, a person creates a device which connects to computer, for example, and they switch off the device with a switch, but it doesn't work because the device keeps working. And in that case, for example, the computer supplies the microcontroller through the data lines, its capacitor charges up, and it just starts working, right? So this is a common problem. Okay, so voltage divider for UART pins, if it was a single-ended connection, it would work, but only in one direction. So, for example, if computer UART to USB outputs, for example, let's say it's output 0 when it's 0 and 5 volts when it's 1, logic 1. You could divide the TX voltage down to microcontroller's level from 5 volts to 3.3, but the problem would be to increase the voltage on the microcontroller's line, because microcontroller will send out 3.3. This computer UART to USB needs 5, so you kind of have to charge up the 3.3 volts to 5 volts to send the data back. So in one direction it will work. It's true, you can use a voltage divider, and just make sure that it doesn't have, yeah, but it won't really, because these are complementary metal oxides and conductor inputs, which don't consume almost any electricity. So yes, in one direction you can use voltage divider, but in the opposite direction, from the smaller voltage to send signal to higher voltage, it can cause problems. Theoretically, the converter can have in its datasheet written that, for example, everything below 1.5 volts is 0 and everything above 1.5 volts is 1. So 3.3 volt level might be sufficient to signal to the other chip. But for example, if the chip says that it needs 4 volts to consider it as high, but your microcontroller only outputs 3.3 volts, then it will not work. So sometimes it works, sometimes it doesn't work. And I've actually had one application where I did exactly that because I wanted to go cheap, and I checked out in datasheet that the receiver only needed 2.5 volts for high, and microcontroller was 3.3, so it's enough, and I could just connect them directly. So yes, you can use also that instead of expensive that thing. Yeah, exactly. Okay, so I have told you about this phenomenon where you can accidentally supply the chip through data lines. This is a real common problem. I've seen, for example, in one case, one guy had a device which was battery powered, and it had also a sensor, actually a very similar case to this, and the device was battery powered, and the microcontroller says the device to turn off, but after 2 weeks the guy tries to turn on the device, it doesn't turn on because the battery is empty and he can't find where the leakage is. And it just turned out that yes, through UART pins, he was supplying the sensor all the time, and so the battery discharged. So yeah. Exactly. And you can actually check out the voltage threshold of a processor in its datasheet. Let's see. For example, this Silicon Labs, this reference manual, I need datasheet. Close all. I don't have datasheet on my desktop. So EFM32 zero gecko datasheet. An example microcontroller in its section about general purpose inputs outputs in electric characteristics. Let's see, where is it? GPIO. Come on. Frequency and voltage levels on GPIO. Okay, here it is. Usually there is a section in chip's datasheet GPIO, and here, for example, it says input low voltage is less than 0.3 times supply voltage. So for example, if you have 3.3 volt power supply, if you multiply it with coefficient 0.3, then basically everything that is under 0.99 volts, basically everything that is under 1 volt will be considered as low, as logic low. And everything above 0.7 power supply, so 3.3 times 0.7, everything above 2.3 volts will be considered high. Everything in between is not really a stable input, and it can switch the level to the opposite. So it's not really stable, so it shouldn't be allowed there. So yeah, this is about the voltage levels. So I guess I have told you maybe something you already knew, maybe something new about this UART connectivity. And of course, when you get the development kits, you will have opportunity to try to use them and send some data and receive some data back and forth with the computer. Okay, so do you have some questions?